clearly enough. We could see it.
Okay, so so this image was already shown. With these elements, we will not be able to implement it, and this is where I'll give you a little bit of background. So urinals and a set of reactors that. Okay, here we go. So microbial electro-concentration of what the technology is about. You can see here line and a lot of the calcium and magnesium salts, including struvite precipitate. We are moving ions as well. So we have a cation exchange membrane, and what we should aim for is to make the circular economy at cities. So the main activity is this center one. Thanks for your time.
Thank you. Still the same?
Okay, so I'll just unplug.
We could see it clearly enough. Stefano. I think it was okay to.
Yeah, that's
fine. Yeah. That's good.
Does it work?
Yes.
Yep.
Okay. Yes. I haven't switched it on for too long. Okay, so nice to see you, everyone. Most of the people here already know me. For those who don't know me, or for those who have forgotten, Stefano Freguia. I'm at Department of Chemical Engineering at the University of Melbourne, where I've been for the last 2 years. Before that, I was at UQ for about 10 years. So here, do you actually see Cara in the corner, or is it just me?
Yes.
Yeah, so the image in the bottom right corner is Fisherman's Bend campus at Melbourne. So this would be Melbourne University's new campus to be delivered approximately in 5 or 6 years' time. So this will be the target of a potential future trial of urine diversion with the technologies that we are currently developing through NICE. We would have liked to have that as part of NICE, but the timing is not perfect. But certainly there would be follow-ups beyond NICE, and this would be a target site for implementation of a larger scale trial, perhaps. So I will be talking about the University of Melbourne projects within NICE, what we're planning to do. Before that, I'd like to move back to an introductory note. Oh, there you go. So this image was already shown, by Sean. And this was really keeping us very busy a couple of years ago while we were planning the planning phase for the hub. So when I met Sean for the first time at the conference dinner in December 2019, we started discussing about our respective research. The focus quickly shifted towards urine, which was really high in our rank of topics of interest. And we started to talk about our technologies and what needs to be done to improve it. And then soon enough, we realized that we were really almost entirely focused on this bit, so urine processing. And as engineers, that's what we do. But we came to the realization that if we are going to implement this concept of harvesting nutrients from urine, technology is not going to be the limiting step. Although there's still a lot of questions to be answered, a lot of development to be made, we realize that we can't achieve implementation unless we address all these other aspects. And so we mapped it out and realized that urine collection, as well as making optimized and commercializable fertilizers, and fertilizers that are usable and effective on target plants and crops. So without these elements, we will not be able to implement it. And this is where we started to map out the work of NICE, together with this outer ring, which includes the very important whole of systems economics. This is something that the industry partners asked us from the very start. How much is it going to cost? Is it going to make economic sense? And particularly for this topic, acquiring not only regulatory approvals, which are essential, but also the social license is highly important. And so we realized our expertise is not enough. We should not go for another linkage project. So what we should do is to try and put together something bigger. And this is where the idea of the hub was created. Obviously, urine is a big part of this hub, but this is not the only place we're going to look for nutrients. However, the work that we'll be doing out of Melbourne is mostly focused on urine as a source of nutrients. So I'll give you a little bit of background. So the technology that we'll be further developing and mainstreaming, perhaps, as part of NICE out of Melbourne is coming out of a previous ERC linkage project between urban utilities and UQ, which was my previous working place. And so out of that linkage, we developed a small-scale trial at Luggage Point treatment plant, where we had a dedicated toilet block with waterless urinals and a set of reactors that we tested and optimized over the duration of the project. So this was successful and attracted media attention. Urban Utilities was very happy and they were interested in continuing, but also they were concerned that another technology-oriented project was not what we needed. This is what they also wanted, something bigger that that includes not only technology, but also social, economic, and agri aspects. And so they quickly agreed onto the idea of supporting the hub. So now, what is this technology that we have developed through this project, and why are we pursuing further development through the hub? So here we go. Got stuck. Okay, here we go. So microbial electro-concentration, which was affectionately named Ugold, similar to Sean's technology URVAL, which identifies the value in urine. We identified the fact that urine is so valuable that can be considered gold. So we won't really deep dive too much, but a little bit to give you background of what the technology is about. You can see here what's inside one of those cells that you've seen in the picture in the previous slide. So this is an electrochemical cell with an anode on the left and a cathode on the right. So this is like the same effectively as a battery or a fuel cell. It's really a fuel cell rather than a battery, where we feed urine as a fuel, and we use oxygen to liberate the energy of that fuel. So urine is a fuel because it contains a lot of organic matter, 10 grams per liter of organic matter, which is most of which is readily biodegradable. When we collect fresh urine, there's most of the nitrogen in the form of urea, and the organic matter is complex. After a period of time, which if you just let it happen naturally, might take up to a month, but really after you do it in a technologically advanced system, it might take only a few hours or less. The process of hydrolysis leads to quite a few transformations. They happen best in the presence of oxygen, particularly urea hydrolysis to ammonia. And with that, the pH goes up to 9, and a lot of the calcium and magnesium salts, including struvite, precipitate out, and we can just already harvest those immediately. That's quite a bit of the phosphorus already, by the way. But then the nitrogen is really staying in the liquid phase. So this technology is really targeting the nitrogen primarily. So through the movement of electrons through a circuit, these electrons are generated from the oxidation of chemicals in the urine. We are moving ions as well. So we have a cation exchange membrane and an anion exchange membrane. And similarly to what happens in electrodialysis, we're moving positive ions into a compartment in between the two electrodes, and negative ions as well, moving that way from the cathode side to the middle compartment. So this way, we're able to harvest ionic species, and actually the nutrients that we're targeting are all small ionic species and are selected for in this system. So the beauty of this is that it requires no chemicals, no process controls, as it's self-controlled, and in an ideal world, no power. We did demonstrate it with no power in the lab, but at very low rate. So, yeah.
Stefano, you have 5 minutes more. Remaining 5 minutes, yeah.
Okay, so let's wrap up the next slide. So this is really good for a decentralized process, because you don't want to have a lot of controls and maintenance issues. But however, we moved away from the no power because it was working too slow. We added a bit of power, we're making a bit of hydrogen at the cathode. That hydrogen can actually be recovered and used to supplement some of the energy requirements, so improving the energy efficiency there. And the rates then go up quite a bit, so that the system is nice and compact. What we achieved from that trial is that the urine was concentrated by a factor of, so the volume was reduced by a factor of 10. Concentration of key nutrients was increased by a factor of 3 to 5. We have recovered up to 65% of nitrogen. There was no problems with the pathogens because of the biocidal conditions that are created in that mid compartment with a lot of ammonia. Good rate at power consumption, which might not mean much to you, but what is important is that this is less than the combination of the energy needed to denitrify, remove nitrogen in the treatment plant, and the Haber-Bosch energy required to make ammonia in the first place. So we're better off than where we are at the moment. So that's the key. The product that we made is liquid, which contained all the key nutrients at the concentration which are still a bit low for liquid fertilizer markets, but they are in line with the low end of what you can find in the liquid fertilizer market, also including organic matter and a lot of trace elements. So we cheered to that, and also did some home-based trials. Because we're running out of time, we're not going to talk too much about micropollutants, but this is also another key question: what happens to the antibiotics and all the other stuff that goes through our urine? The beauty here is that because of those membranes only allow small ions through, we removed 99% of what we found for most of the micropollutants that we were able to find in there. Only a few of them broke through, and those are not the ones of main concern, although this was just the result out of one trial, and this will need to be further investigated. I'll skip on this one, otherwise I won't have time on my main slide. But basically, this is just to say that we have a market for liquid fertilizers. It's worth quite a bit. So about $500 million, which is actually 1/3 of the total fertilizer market in Australia. That's because not in terms of mass, but in terms of value, liquid fertilizers are more highly priced. And they also have a lot of advantages compared to solid fertilizers. With the advent of urban farming and the need of liquid fertilizers in urban parks and gardens and lawns, I think what we should aim for is to make the circular economy at city scale, so that we are actually harvesting nutrients where the nutrients are consumed and released. So the cities are the places where we have a lot of urine, and the cities are the place where we can implement urban farming, minimizing the movement of liquid along large distances. So what we're going to do at Melbourne University as part of this hub, there's quite a few activities. So the main activity is this Center 1, Project UM1, which will be undertaken by a postdoc, which is field testing and mainstreaming Ugold, delivering a 300 liters a day pilot at the Brisbane location. This will be an outdoors location. We still cannot disclose it, but it will be a location of primary visibility. So that's basically taking what we had, improving it, and just putting it to the test of the real world in a public toilet. Then we don't have all the answers to technological improvements, but we will be. Are we out of time? It's just a couple of minutes. Improving rates, reducing power consumption, and increasing nutrient recovery. Because one of our partners is interested in sludge digestion side stream, we'll also target that for some of the trials to see how much nutrients we can harvest in a centralized system. 3 PhD projects. One already has a name on it. Negar is actually in the meeting. Looking at fouling management, response to real-world factors like temperature, pH, and chemicals, and also strategies for startup and downturn, which are all real-world issues that we haven't looked at in details. Other PhD project on the right, the effects of urine diversion on sewage treatment plant performance. So we're going to take urine out of the sewers. How is that going to affect sewer processes? How is that going to affect sewage treatment plants? We believe that the energy consumption will be reduced, but also what are the effects on greenhouse gas balances and micropollutants. And finally, the project will be based on post-processing, so that whatever comes out of these pilot reactors can be post-processed into something that is more desirable for application in agri-horticulture or hydroponics, or and also more concentrated to be more easily marketable. So that's what we plan to do, and I believe that there's a lot of interactions possible with other universities based on this. These are the partners that are funding this part of the world, particularly urban utilities, IXOM, Southeast Water, and also our technology partner, AJJA, and NutriTech Solution as our small boutique fertilizer company. So with that, I have concluded my contribution. Thanks for your time.
Thank you, Stefano.